Hello, this talk is going to be on Java Language Futures, the mid-2020 edition. My name is Gavin Bierman, and I'm a consulting member of technical staff here at Oracle, and I work in the Java platform group. I just want to say before I start that we want to hear from you, so please feel free to ask any questions in the chat window at any time. And there'll be an expert on standby to answer your questions. Now, I have a lot of material to get through, but I am hoping to finish in time so I can answer some questions at the end too, if there are any. Now, this is by definition a forwards-looking talk. In fact, none of the technical details, the language features that I'll talk about, are actually in the Java language. They're still in preview. So this slide, the traditional safe harbor slide, is very important. All of these features could change, so please be aware of that. Just wanted to give some context about this talk. So of course, one could give a futures talk at any point in time, and both I and my colleagues do this talk that's given quite often. Now, many of the projects that we're involved with designing new features for Java take several years. And so there's quite an overlap between some of these different versions of this talk. So at any one time, this talk presents the particular snapshot of the features in question. So perhaps you've seen an earlier version of this talk, and some things you might have seen before, but I hope that some things you haven't, and indeed some things might have changed. And before I dive into the technical details, I do want to spend just a couple of slides considering some of the philosophy that we have around designing new language features for Java, and also some of the methodology that we've adopted recently. Okay, I'm sure you're aware that Java is 25 years old this year, which is fantastic. Now, for a person, 25 is not that old, but for a programming language, 25 years is quite an age for a programming language. And indeed, Java has been declared dead many times, but we are still around and we're a very popular programming platform. And it is our intent to make Java popular for at least another 25 years. Now, how are we intending to do that? And really, this is a sort of multi-pronged effort. Firstly, we need to stay relevant to the problems that people are actually wanting to solve right now. And that's quite important because the problems that people are using Java to solve today is quite different from the problems that people were using Java for when Java first came out. So we keep a close eye on the sorts of applications people are using Java for. We're lucky that we have lots of Java developers inside Oracle, but we have lots of colleagues elsewhere. We're very much aware of the sorts of applications people are using Java for today, and we are keen to make Java relevant and useful for those modern applications. Perhaps less obviously, we need to keep Java relevant to the hardware platforms that people are actually using today. And again, this is hugely different from the platforms that the Java language was developed on initially 25 years ago. If you consider your laptop on your desk right now, it has many cores. My laptop has 6 cores, which almost certainly none of the original designers of Java had. And it has many layers of cache, and the cache sizes are quite different and their characteristics are quite different. So we need to keep Java running efficiently and effectively on the hardware of today. We have ever-rising developer expectations of Java. I think this is both because training for Java is better than it has been before, and also because developers are exposed to many new languages nowadays, and they come expecting Java to have features that they've learned about from other languages. Another very important aspect of Java is that we keep the promises that we've made to our users. This really distinguishes us from certainly academic languages and some other languages. When we make our promises, we keep them. So in particular, promises about compatibility are very important to us, and they're at the core of our design process. I'm sure you've heard that we changed the release cycle for Java. Before, Java releases came every 3, 4, 5, 6, 7, 8 years, whenever the feature was ready, and they tended to be sort of big bang releases, so huge changes to the language occurred in each release. And we've changed about 2 years ago to a 6-monthly time-driven release cycle. So every 6 months, there's a new version of Java, and features are late bound to the release. So a feature is only released when it's ready. Now, the nice thing of having these frequent release cycles is that if a feature is not quite ready, it's not too long to wait for the train, for the next train to come, only a few months. So this enables us to release a feature only when it's ready to ship. Another change that we've made is to release language features as preview features. So a preview feature is complete, so there's a full implementation. It's not a half-baked idea. There's a full implementation, there's a full specification. Because we talk closely with vendors of IDEs, there's often IDE support already, but this feature is not final. You have to explicitly opt in to use a preview feature. So you have to use the enable preview flag on both Java and Java-C. So you can't use a preview feature by mistake. We certainly don't recommend that you use it for production use because, of course, we might change them. And the intention here is that we want people to try them out and to give us feedback. And so far, many features have had 1 or 2 rounds of preview before we finalize them. This is fantastic because now we get a chance for our customers to try new features, give us feedback, amend the designs if necessary, and give people further time to try the amended designs before we settle on finalizing a feature. So this week, JDK 15 was released, and there are many fantastic JEPs in that new release. But in terms of the language, there are 4 JEPs that address new language features: records, pattern matching, for instance, of sealed classes and text blocks. Now, I don't have very much time today, so I'm only really going to have time to talk about 2 features. So I've picked the first 2 preview features, as these are the most forward-looking features, and I hope the most exciting in that respect. But of course, you can join various mailing lists. All the JEPs are online. There are experts to talk to on the mailing list, so you can get details of all these JEPs. So let's start with the first language feature, records. We're all familiar with writing classes which are really just fairly dumb aggregates for data. We all know how to do it, and those of us who've done it have noticed that you have to write quite a lot of boilerplate code. And writing these is just no fun, basically. Even if the IDE, your favorite IDE, writes a lot of the boilerplate for you, reading these classes is still pretty tedious. Now, the problem with tedious code is people's eyes tend to glaze over, and this is where bugs end up residing. So let's have a look at a very simple example. So I want to write a very simple aggregate class. This class is called point. It contains 2 integer values, x and y. And I've been to a good course, so I want to make these immutable. So I'd write this as a class containing 2 final fields. But of course, that class is not complete. I need at least a constructor. So I need to write a constructor which takes the XY parameters and assigns them to the fields. Very boring, very automatic. Now I could stop there, but I've been to a good object-oriented programming in Java 101 course, which has reminded me that, oh, I really ought to write the equals method for my class. So I need to override the equals method from object. And again, the definition of this method is not very difficult. It's automatic. Most equals methods look the same. And it's just derived on the content of the class. But I remember that I'm not done. I should really define the hashcode method. And again, the definition of this method is pretty automatic, but I have to write it anyway. And again, I realize, oh, I should have really overridden the toString method as well. I'm not quite done because I realize that it's much better to have made my fields private and declared accessors for those fields. Now, at this point, I really am done, but this code is getting quite long, and this was supposed to be just a very simple class containing 2 integers. So what's the semantic content of this class? Well, the semantic content is just that it contains 2 integer values x and y. What if there was just some way that I could declare only the semantic content? I might imagine I had some way of saying that this was a special sort of class, let's call it a record, and I put this data, this semantic content about having 2 integers in a header. So these are now sort of components of the record. So they appear at the front of the class. So now I don't need the field declarations because that's implicit in writing this header. Now, once I've done this, I can start taking a look at the contents of the class declaration, and I can see that much of this could be automatically derived from the semantic information that I've put in the header. So firstly, I certainly don't really need the declarations of these accessor methods because that's completely automatic from the declaration I've made that this contains 2 private final fields, x and y. I can also see that I don't really need the constructor because the contents of the constructor body are derived again entirely from the declaration I've put in the header. And similarly with the equals method, this could be automatically derived from the semantic information I've put in the header that we have 2 fields, int x and int y. And you've guessed it, I could have done the same for the hash code and the toString method. Really, the only semantic content of the class is that it contains an x and a y, which are both integers. So let's just move this to the middle of the screen. So really, this is what I want to declare, and I want all the other stuff to just be automatically derived by the compiler. So this is a record. That was fast. So let me just recap. What's a record? So I think of a record as being a simple aggregate, and it's really about the data, the whole data, and nothing but the data. So it's quite transparent, and I'm a civilized programmer, so I would like all my components to be immutable. The best way to think about records, if you're familiar with similar notions in other programming languages, is that it's a nominal tuple. So both the aggregate, the record itself, has a name, and the components are accessed by name, not by their position. Now, this is similar to choices that we made for Lambda, where we could have chosen a structural function type, but we didn't. We chose a nominal function type. Nominal types are the essence of the Java type system. And so we have adopted a similar thing here for records. Now, there are actually many different notions of data carriers, and that enabled us to, or caused us to have quite a lot of discussion about the design process. But we're confident that we've hit a sweet spot now, and feedback for record classes has been very positive. So I don't want to give you the impression that all record classes is about reduction of boilerplate, because it's not really about the boilerplate at all. A record is about a semantic declaration that I am just a carrier for the data, and here is the declaration of the data I wish to carry. And this is kind of another design philosophy that we have, that really, if you pick the construct with good semantic content, then the benefits kind of come for the ride. The boilerplate takes care of itself. The opposite is rarely true. If you start off just trying to eliminate boilerplate, you very rarely hit on a well-defined semantic concept. And this is sort of analogous to some of the design decisions that were made over enums. So enums are just a class, but we are willing to trade some control over the creation of instances, and we get a lot of functionality for free. And it's very similar for records. But I do want to emphasize that records are just special classes. They are real classes under the hood. So just like a class, here I've got my record point class, you can declare methods. So it's no problem for you to declare here a normalization method. All the rules for writing methods in classes carry over to records. Similarly, you can write your own constructor. The compiler will give you a constructor if you don't, but if you declare your own canonical constructor, and here I mean a constructor whose formal parameter list matches the header, the record component list in the header, then you can write your own. So here, for example, I've got a range record class that takes two integer values, low and high. And we need to write our own canonical constructor because we want to exclude illegal instances. So in particular, if the low value is greater or equal to the high value, then we want to throw an exception. So the interesting thing to note here is that when we've used records ourselves, we've performed experiments with them, we've noticed that when you have to declare your own canonical constructor, you're typically doing one of two things. You're either verifying the arguments, which is what we're doing here, or you're normalizing them in some way before we store them to the field. So we do this sort of boring boilerplate code at the end. And we've noticed this come up a lot. So in fact, so much so that we decided to support a new compact form of declaring a canonical constructor. So as you recall, a canonical constructor is one whose parameter list matches the header. So if that's the case, you can remove the formal parameter list entirely. The compiler will insert it for you. And you can remove the assignment to the fields at the end. So we offer this compact form of a constructor for records. And again, the point of this is to expose the intent of the constructor. The intent of the constructor here is to verify that the values passed are correct. The other more boilerplate stuff about assignment to fields is dealt with for you by the compiler. So let me give you a simple use case for records, which is really rather nice. So we're defined a pair of static methods over iterables that takes a comparator. And the first method returns the minimum value according to that comparator, and the second method returns the maximum value. Now, this is familiar to many people, and it's a long, old complaint that this sort of API design encourages inefficient code, because if you want both the minimum and the maximum value, you have to make two passes over the data structure. And indeed, this has led to people in the past requesting for multiple return to be added to Java. But now with records, we can do this straight off the bat. We can define a record, say, called min-max, which takes those two values, the minimum and maximum, and then we just make a new method, min-max, which returns the pair in the record value. Now, this is quite a nice benefit of records, because what we've done is reduce the overhead of declaring a new data abstraction, which hopefully will enable us to write clearer APIs that will result in better client code. Now, you might be wondering, well, couldn't we have done this before? And of course we could have done. We could have declared a class. But as we've seen right at the start of this discussion, declaring carrier classes is quite painful, has been quite painful, and records is there to address that sort of problem. Okay, so let me switch gears and look at the second JEB, which is for pattern matching. We've all written code like this, where we have to test and extract values. And we do the test by using an instance of, so here we're checking whether the object obj is a string. And if it is, then we have to cast it to string to get the string value out, which we do with an assignment. Now, this sort of repeated use of string is rather irritating. People complain about it. So you see we have to say the same thing 3 times. And it sort of obscures the code that you're actually trying to do. And so it's, again, an often requested change to the language to address this sort of boring boilerplate. Now, we could have done something like flow typing. We could have realized that inside the then block, obj has the type string, and we could have changed the type of obj within that block. But we think we found a better answer, which is to use pattern matching. Now, pattern matching fuses these 3 things you see in circles here. It fuses the testing whether something has a type string, the conditional extraction, so if it has, then we extract out the string value, and also the binding of variables. So let's see an example in action. So here's how we use pattern matching in instance of. We say, is obj an instance of the pattern string s? Now, the semantics of this is that it tests obj to see if it's of type string, and if it is, and only if it is, then we assign this pattern variable s to the value of the string. So you're free to use the string s in the then block. So now all that cast and that temporary assignment has disappeared. It's actually just contained in the semantics of pattern matching. So we're hoping that many, many of the casts in your Java code will disappear with this feature, which will be a nice thing. And another pleasant feature of this design is that pattern matching works very nicely with other expression forms that we have in the language. So here I've taken the equals method for a class of case-insensitive strings from the book Effective Java, and I've just rewritten it using pattern matching. So the idea here is that we take an object, we check to see if it's a case-insensitive string. If it is, we'll bind it to the pattern variable CIS, and then we'll return whether the string s is equal to that CIS string that we've extracted. And because of the short-circuiting behavior of the AND operator, we know that the CIS string will be bound to a value. There's lots more information about pattern matching. Brian Goetz and I have written a whole series of papers on how we see pattern matching fitting into Java. But let me just show you a couple of examples of future extensions of pattern matching that we hope to add to Java. So one is obviously adding pattern matching not just to instance of, but to other constructs. So the first candidate for this would be switch. So now we've got a constant here, type object, and we can check, we can switch over it according to whether it matches these type test patterns. So this is like a type switch, which is an often requested feature of Java, but we're using patterns, not just types. So we get the binding variables to use in the right-hand side of the case rules in this case. So it really simplifies a lot of switch code. Here's another nice extension that highlights that pattern matching and records, in fact, work very well together. So let's imagine we have an interface shape and we have two record classes, circle and rectangle, that implement that shape. Now, we're now free to, we could imagine an enhanced form of pattern matching called deconstruction patterns. And the idea here is that the test that we're encoding in the pattern is much richer. So here we're testing whether a shape is not only an instance of a circle, but also, if it is, we would like to bind the center and radius pattern variables to the values contained in center and radius. So again, this removes a lot of boilerplate code. And this sort of deconstruction pattern, it kind of has the feel of the opposite of a constructor. And we can keep going. You might recall that the circle record, the center is in fact of type point. And we can nest these deconstruction patterns to form quite complicated patterns that again are just contained in the declaration of the pattern itself. So in this test here, we're testing whether a shape is an instance of a circle, and we're testing whether the first component is a point, which in this case it always is, and if it is, then we'll bind the pattern variables my x and my y to the contents of the point. Okay, so wrapping up, I hope that this has convinced you that we have a rich feature set in the pipeline for Java. We have the first set of sort of significant language features from Project Amber arriving. So I mentioned today records and pattern matching, but I didn't have time to mention switch expressions, which shipped in final form in JDK 14, sealed classes, which are previewing in 15, text blocks, which are final in JDK 15. And I've given you some hints, but we have lots of others that are coming in JDK 16 and future editions. And I, of course, didn't have time to mention other exciting projects that are going on in the Java group. So Project Valhalla, which addresses some of the concerns I mentioned right at the start of this talk about targeting more modern hardware, really are now starting to bear fruit. And many years in the lab, but now you can download code and see it run of various prototypes of Project Valhalla. And projects Panama and Loom. So Panama is addressing native interop, and Loom is a lightweight threading model, also making tremendous strides. So it's a very exciting time for the Java language. So at that point, I shall wrap up and we shall take a look at some of the questions in the chat. So I've got a question here, which is, why didn't we just add tuples to the language instead of adding records? So it's a good question, and we had quite a lot of discussion about this. But I think in the end, our feeling was that Java is a nominally typed language. We've resisted adding structural types up to this point, and nominal types seem to be a better fit for the language as a whole. So in the end, we decided that the advantages of nominal types are there for us to see, and we didn't want to move away from that. Okay, So, technical questions. So, what about nested records? Are they static? So, yes, they are. They in fact have to be static because of this invariant that we want records to declare in their header in that record component list uh, the entire contents of the record. So, the data and nothing but the data. If they weren't static, then they would be able to capture things from their outer context, and we don't want that. We want their declaration to be complete. Okay, and then we've got a question asking whether we could have deconstruction patterns for normal classes, not just for records. So I showed you them for records earlier. Now that's a very interesting question, and yes, we think that we will be able to do that. So I mentioned that we've written some documents, myself and Brian Goetz, which you can search for on the web. We spell out there a sketch of how we think standard classes can support pattern matching and deconstruction patterns in particular. Okay, and I've got another question, which is asking about sealed classes. So this is another JEP that is in JDK 15. So I was hoping that someone was going to ask me about those because I have a backup slide for that. So let me move to this. So I'm sure you're all aware that Java really is all about the inheritance. So it's about inheritance of classes. It's an important aspect of object-oriented programming and design. But interestingly, Java gives very, very little control of inheritance to the programmer. So you can either declare that nobody can inherit from you by declaring yourself as being a final class, for example, or you can't, and then anybody can extend you. It's not a very flexible system. And there are a number of cases where this is not good enough. So we've noticed in some of the APIs, in fact, that we've written and also our customers have written, that they want to be able to declare a type in their API, but they want to themselves implement the only subtypes of that type. And that's just not possible to do directly. You have to do it by clever encodings. And another thing is that we might hope that there was some way, say in switch, or if we were switching over types, that if you knew that there were only limited subtypes, that the compiler could exhaustively check for you that you've covered all of those cases in your switch and nothing more, nothing less. Now, obviously, if the language supports unlimited inheritance, then that's not possible. So what sealed classes are about is allowing a class or an interface to actually explicitly declare all of its subtypes. So here we have the example that I had from before of an interface shape. Let's say we're only allowing two record classes to implement that shape, circle and rectangle. And we're proposing that actually the interface itself can declare exhaustively all of the types that are allowed to inherit from it. And in fact, the compiler will check that those classes do actually extend you. So there are no surprises from anybody. And we think that this is an extremely useful feature and also mixes very nicely with pattern matching and other extensions that we plan for the language. Okay, so at that point, I think I am out of time. So before I go, I just want to encourage you to consider one of the next sessions, two fantastic sessions following this one. one on ZGC by Per Leiden, the new garbage collector in Java, and also another session by Sean Mullen and Chris Rees talking about how to make your Java applications secure. So please visit the website for the agenda for the rest of the day, and also click then the join button on that agenda to join either of these two excellent upcoming sessions. So with that, thank you very much.